Okay, let's start. Welcome everybody back to ENLA, the online seminar series on numerical linear algebra. My name is Daniel Kressner. Today's Zoom questions will be handled by Bart van der Eycken, and the YouTube questions will be handled by Jörg Liesen. It's a great pleasure for me to welcome Des Higham from the University of Edinburgh. Des Higham is one of the leading researchers in numerical analysis. He's well known for his book co-authored with Nick Higham on the MATLAB guide, several other books. He's well known for his work on ordinary and stochastic differential equations, and more recently, network analysis. And among the many highlights of his publication records stand out two or several SIME review papers, one of which was on the numerics of stochastic differential equations, which had a huge impact on how we view numerical methods for that purpose. And more recently, and I think that has become very popular, is his co-authored SIME review article on an introduction to deep learning for applied mathematicians. Today's talk will be on net in the direction of network analysis, concepts and algorithms for higher order networks beyond pairwise interactions. So please go ahead, Des Higham. Looking forward to your talk.
Thank you, Danielle, and it's a great pleasure to be given this opportunity. So I'm assuming that you can hear me, and I'm assuming that when I page down, you can see the next page. Good. So I'm going to start with quite a bit of introductory and background material, just to try to make the talk as accessible as possible. I appreciate that many people listening will not be network scientists, and I'll present things from a linear algebra perspective. I'm sure you've all seen these pictures of large, complex networks, and the kinds of things that we like to do is to summarize what's going on in these networks, try to reduce information down to something manageable, try to interpret those summaries, maybe explain how these networks arose, that's a modeling issue, and then apply algorithms to find patterns and possibly make predictions about how the network might behave in the future. But this whole network idea is really based on graph theory, which looks at nodes and edges involve pairs of nodes. So this is very much using pairwise information. So we're told whether two nodes have some sort of connection or not. And more recently, several authors have pointed out that the kind of data that we're looking at quite often has a much richer structure to it. Although we think in terms of pairwise interactions, we really have more complicated or higher order information. So for example, when you go to the supermarket, you buy a basket full of products. If you bought milk, eggs, and cheese, you could put an edge in between milk and cheese and milk and eggs, but really that's a triangle, that's three things. So the data really is those three items in the basket. And when we look at co-authorship networks, we have a list of co-authors, and you can think of them as pairwise connected because they've jointly worked on a paper together, but really the list of co-authors is the ultimate piece of data. And thinking of the spread of disease, for example, people interact with each other, but they tend to do that within groups. So we can talk about households or groups who work together. So very often there's a higher order level of connectivity, and a simple pairwise or matrix description doesn't necessarily capture everything that's important. And so, as I said, there are lots of authors looking at this at the moment. The top picture there concerns motifs. So given a network, you can look for the existence and the relative frequency of different types of subgraph. The middle picture there takes the hypergraph and hyperedge viewpoint. So the vertices here, for example, may represent people that write academic papers, and the red hyperedge has V1, V2, V3, V6, and maybe those four people wrote a paper together. So a hyperedge connects more than two nodes potentially. The picture on the bottom there really arises from a more topological perspective, where they like to think in terms of simplices. So for example, a 3 simplex involves 4 nodes. So it's a set of 4 nodes But from the topology perspective, the simplex includes, there's a sort of downward closure, so the 3 simplex includes each face. So the 2 simplices consisting of triples of nodes would be part of that description of the 3 simplex. So these are all slightly different viewpoints. And if you wish to follow up on this, I've listed there some of the recent literature, which again, as I said, takes slightly different viewpoints potentially. My view is that the hyperedge and hypergraph setting is the most relevant as far as I can think in terms of the applications that are of interest to me. And the final article there really discusses the different types of representation and which ones might be most appropriate. For my talk, we don't need to get into that debate. As I'll mention later, we can handle either the idea of building motifs from pairwise interactions or being given that higher order information. So the algorithms I'm looking at can handle either scenario. So I'm going to focus on just one level of higher order interaction, although we're currently working on the more general setting. But to keep things simple now, let's look at nodes, edges, and triangles. So triangles are triples of nodes which are connected. And they could be given to us as part of the data. So these 3 people wrote a paper together. These 3 products were purchased together in a supermarket shop. Or they could be built from the edges. So we know that I and J are connected. We know that J and K are connected. We know that K and I are connected. So therefore, we can build a triangle from those 3 pairwise interactions. So either case is fine for what I'm going to talk about. And as I said, we can generalize this to the higher order case. That's current work in progress. So here's what we're going to discuss. I'm going to look at things called centrality measures and related quantities, and we're going to use the idea of mutual reinforcement to make our definitions. Tensors are going to arise because we're going beyond pairwise. The algorithm I'm going to discuss can be thought of as a generalization of the power method into a nonlinear setting. And I'll show how these ideas work in a particular application, which is link prediction. And this is joint with Francesca Arrigo at Strathclyde and Francesco Tudisco, who's at the Gran Sasso Science Institute. And we have a public domain open access paper with more details. So here's a little bit about the notation. I'm focusing here on undirected networks, but everything I say generalizes to the case of directed edges. So you can put arrows on these edges and everything still works, but we are assuming that the edges are not weighted. So we're focusing here on undirected, unweighted graphs with little n as the number of nodes, and capital A is the adjacency matrix. So Aij is 1 if there's an edge connecting I and J, and is 0 otherwise. The boldface 1 here is the vector of 1s. So A times 1 is doing the row sums or counting edges out of each node. So the vector D there is the degree vector. The ith entry tells you how many edges node I possesses. And if you think in terms of friendships, if these are people who know each other, then you could argue the more people you know, the more important you are. So if you wanted to say, what are the important nodes in the network, then you could argue it's the ones with the highest degree. Degree is therefore an example of a centrality measure. It quantifies how important each node is. And generally, such a measure maps the adjacency matrix into a vector with non-negative entries, and the ith component tells you how important node I is. Degree, of course, is a fairly crude measure of importance. So here's another standard measure of centrality called Eigenvector centrality, and it uses this idea of mutual reinforcement. So it doesn't doesn't only matter how many people you know, it also matters how important those people are. So with this kind of argument here, we might say that the importance of node I is proportional to the sum of the importance of all the people connected, all the nodes connected to node I. Okay, now of course this is a recursive definition because we don't know how important these people are, but we can think of this just as a relationship, and if 1 over lambda is the quantity that relates these two, the proportionality constant, then lambda then becomes an eigenvalue of the matrix. And because we want non-negative measures, non-negative values, then X must therefore be the Perron Frobenius vector of this matrix A. You can also motivate this from an iteration point of view. If you randomly assign non-negative values at the 0th iteration and then perform this iteration over k, so at step k plus 1, node I picks up the sum of the centralities of the nodes at the previous iteration, then this is simply the power method. And that will therefore, especially if you normalize sensibly, it will therefore converge nicely to the dominant eigenvector of that matrix A. So it's another way of motivating eigenvector centrality. And I wanted to point out at this stage that you can also think of this vector X as solving an optimization problem, this Rayleigh quotient. And this is not a convex objective function. So although the power method converges, it's interesting to me at least that you're not solving a convex optimization problem. But convergence is guaranteed as long as you start off with an appropriate initial condition. So eigenvector centrality was proposed in the network science literature, and that's the typical reference that people make when they discuss this topic. But it was recently pointed out to me that these ideas go much further back. So you can go back to 1895, and this idea for measuring importance among pairwise relationships was put forward. And the context might be surprising if you haven't come across it, and it is the world of chess and chess tournaments. So when people play each other at chess, if you win, you get a 1 point. If you draw, you get a half. And if you lose, you get 0. And then you can simply add up all your points after you've played each other in a round-robin tournament. But it was realized even back then that somehow beating a strong player was more important than beating a weak player. On the other hand, how do you know who are the strong and the weak players until you've done the ranking? So it's a very similar question to the one we just looked at the top of the slide. So it was Edmund Landau, and this is the person who, among other things, invented the Landau, the big O and the small o notation, who proposed this idea, building on some previous work. If you think of this, the matrix of scores against all your components, then that matrix times the vector of 1s just adds up all your scores. If you then iterate, take A times that vector, then you're adding up a weighted version of your scores where you're allowing for how strong or weak those opponents were. And Landau had the idea of iterating. And this is even before Perron Frobenius theory was developed, that Landau had this idea of somehow performing a power method type iteration. And there's a reference here where you can follow up on the details. And while we're on the topic of eigenvector centrality, I wanted just to make a little digression. So this is some work that's came out of some other work I'm doing at the moment, which is currently being written up. But we came across this graph. So here's an undirected graph with 11 nodes. And for those of you that have some network science experience, the question I want you to think about, or maybe you want to write down the matrix and do some computation in real time, and I'll discuss this at the end. The question is, which of these nodes do you think is going to be the most central according to eigenvector centrality? We're calling this the squid graph because we think it looks a little bit like a squid. So just looking at it, node 1 has the highest degree. That has 5 edges. But node 6 is quite central, and node 8 and also by symmetry node 10 have degree 3 and involved in a triangle. Is node 7 more central than node 9, do you think, on this graph? So have a think about that. While you're writing the matrix down, if you want to do any computing, I'm happy to have a break here if there are any questions so far. So feel free to type into the chat if you have any questions.
So far, there are no questions on Zoom.
Right. Okay.
And
so
nothing on YouTube.
Right. Okay. So just write down that adjacency matrix if you're interested, or just have a think about it. What do you think is the most important node in that network? And of course, there's something interesting. Otherwise, I wouldn't be showing you this picture. So another area where this mutual reinforcement has been used, which you may well be familiar with, is ranking web pages using the Google PageRank algorithm. So we can motivate this again through an iteration, and you can think of it as voting. So each round of votes transfers the weight around the web pages. We're dividing by the degree here, so this is more of a random walk type of iteration, or each node has one unit weight of votes to give out. And there's a 1 minus c here. This is a teleporting aspect. So, or another way, in the voting context, we're giving everybody a little bit of weight, and then we're giving them some combination of the weights of the nodes that are connected to them. In a random walk setting, we're randomly walking around the network, picking edges. When we reach a node, pick an edge uniformly across all the possibilities, but also randomly teleport. So randomly choose an arbitrary node with some fixed probability on each step. And again, there's a linear system which describes the steady state of that process. So we can find x by solving a linear system, but we can also think of this as a constrained eigenvalue problem. So we're looking for a vector with non-negative entries which solves this eigenvalue problem. And in this case, we know that lambda equals 1. And it's this eigenvalue setting that we're going to generalize to the higher order case. One more little bit of background. We're going to also generalize something called the clustering coefficient. So this was made popular in a very highly cited paper by Watson-Strogatz in Nature. This was the paper that popularized the small world network model, but they also introduced this clustering coefficient as one of the ways to analyze the model. And this coefficient, it gives you a number for each node, and that number quantifies the propensity of that node to take part in triangles. So more precisely, you look at how many edges are coming out of that node. That tells you how many possible triangles the node can be involved in, and you look at the proportion of those possible triangles which have actually been converted into triangles by that third edge being present. So it's based on this ratio. So di is the degree, so di times di minus 1 over 2 is the number of wedges, that's pairs of edges coming out of the node, and then we compare that with this triangle I, the number of triangles coming out of the node I. This picture here might help to illustrate what's going on. If you look at the green node, it has 3 edges coming out of it, and in this case, both so all the other neighbors are connected to each other, so all the possible triangles are present. So it's 3 out of 3. In this case, the dotted line signifies no edge. So there are 3 neighbors still, but only one of them, one of those pairs has a connection. So there's 1 triangle out of 3. So the ratio is 1/3. And here there are still 3 neighbors, but none of them have mutual connections. So there are no triangles. So that would be c equal to 0. But there's no mutual reinforcement in this definition. So we don't have any sense of whether those triangles involve important nodes. So we think that's a gap in the literature, and we're able to solve it with what's coming next. Okay, so onto the new material. We're interested in incorporating information about triangles into these types of algorithms. So we're going to build these tensors, and I'm going to focus on just a couple of cases. We have more details and more examples in the paper. But here's the simplest type of triangle tensor, the binary triangle tensor. So it has 3 dimensions, and the ijk entry is 1 if ijk form a triangle, and it's 0 otherwise. And as I said earlier, if you're given pairwise information, then you can build this binary triangle tensor just by looking at whether those 3 edges exist in each case. And there are very quick algorithms these days to count and record triangles. But in the setting where you're given triangles as part of the data, then of course we could build the matrix T directly from that data. So either of those settings can be incorporated here. Given this 3-dimensional tensor T, we're going to define an operator which operates on a vector x in Rn. And it returns a vector in Rn, and here's the ith component of the operator. So it's a double sum over j and k of tijk times some combination of xj and xk. And we're introducing the power mean here, mu p, because the theory that we have works generally for any choice of p. So mu p is just a way of combining these 2 real numbers, which will be non-negative in our context. So p equals 1, of course, is the usual arithmetic mean. But this setting also includes the geometric mean and the harmonic mean and the max or the min. Okay, so whenever there's a triangle involving I, j, and k, then node I gets some benefit from the values in the components xj and xk. So we're going to incorporate this into a centrality measure. This is going to contribute to the centrality of the ith node by allowing for the fact that xi may or may not be involved in triangles. And by using xj and xk here, we have this mutual reinforcement that node I can benefit from the importance of its nodes with which it shares that triangle. Okay, so that's going to be the idea. So here's our general definition of our first and second order combined eigenvector centrality measure. So again, it's a constrained, this time it's nonlinear because Tx is a nonlinear operator, nonlinear eigenvalue problem. We're asking for x to have non-negative components, and we're combining these 2 terms, first and second order. So the centrality of node I is proportional to something involving the pairwise interactions. So it benefits from having a pairwise relationship with important nodes, but also something involving these triangle-based relationships. So it benefits from being involved in triangles with important nodes. It's a convex combination. Alpha equal to 1 reverts back to the first order eigenvector centrality measure, and alpha equals 0 is using only second order information. I'm giving the simplest definition here, but we can also replace the matrix A by any other pairwise interaction-based matrix. So for example, the PageRank matrix could be used in there. And we can normalize entries in the tensor T in various ways, and we can also define the entries in various other ways. So have a look at the paper if you're interested in those extensions. But once we've made a definition like this, of course, we're interested in whether the definition makes sense. Does this X exist? Is it unique? And how do we compute it? So that's what we're going to focus on next. And we're going to do something like the power method. And the algorithm works in a similar type of generality. The underlying graph simply has to be connected and also aperiodic for this algorithm to be usable. So I won't go through the details, of course, of the proof, but here's the main theorem. So this constrained nonlinear eigenvalue problem at the top does have a unique solution. And just like the eigenvalue case, of course, it's unique up to multiples with positive entries. And for any starting value with positive entries, we can compute that with a power method type iteration. And this is probably the first thing you would think of if you tried to find a solution to that eigenvalue problem. We simply iterate with our current value to get the next iterate, and then we normalize. But that relatively straightforward approach can be shown to converge. The proof requires quite a few results which come from a recent body of work in nonlinear extensions of Perron Frobenius theory. So I've listed here some of the work that's drawn upon in order to prove this result. So I'll give a couple of examples where I show this algorithm in use and the centrality measure that arises from it. So the first example is one that we made up ourselves. So it's a synthetically constructed network. We wanted just to make sure that we can understand how the second order information is being used and make sure that the centrality measure does take account of that and quantify the effect of this parameter alpha, at least in a simple example. So we built this class of networks that we call wheel networks, where there's a node in the middle, which is the hub node. And this is connected to little m nodes at the next level. So we call these the wheel nodes. And it's connected to them in this way, like the hours on the clock. So we have triangles here. So node 1 is involved in little m triangles involving the wheel nodes. And then each of these wheel nodes is connected with degree 1 to these degree 1 nodes, which we call the leaf nodes. There's a ... here because there's more than 3 of them in general. We're going to put little k of those onto each wheel node. Okay, so these wheel nodes have 3 edges, 2 of them to their neighboring wheel nodes, 1 to the hub, and they also have k edges going out to these leaf nodes. And the leaf nodes only have degree 1. So node 1 is involved in a lot of second order triangle-based interactions. The wheel nodes, each of them is involved in a couple of triangles and then a lot of degree 1 interactions. So the question we're going to look at is how many leaf nodes do you need, or how large does k have to be in order for x2, for x2 to be regarded as more central than node 2 regarded as more central than node 1. So when is x2 bigger than x1? How large does k have to be relative to the number of triangles that node 1 has, m? And we've set this up because this is just about at the limit of what we can analyze analytically. So we can do the linear algebra and we can come up with an expression that relates those 2 centrality values. Okay, so for purely first order centrality, that's the case where the parameter alpha is equal to 1, then you can show analytically that the wheel node beats out the central hub node when k is larger than roughly m squared. In the general setting, where we have this convex combination parameter alpha between 0 and 1, and at least in the case where p is 1, so we have the arithmetic mean as our power mean in the tensor operator definition, then we get this effect x2 greater than x1 when k is above this value on the right-hand side, which is again quadratic, but it has a much smaller leading term in the quadratic coefficient in the power of m squared. And here's a picture just to illustrate how these cases vary. So the horizontal axis shows different values of m. Oops. And remember, m is the number of wheel nodes. And the vertical axis shows different values of k. K is the number of leaf nodes. And the solid line is showing you the boundary beyond which x2 is bigger than x1. So if you fix a value of m, increase k, then you have to cross this boundary in order to make x2 bigger than x1, to make the wheel node more central. So you can see when alpha's 1, you need relatively few leaves to make those wheel nodes look more central. When alpha's a half, you need a lot more leaves, and when alpha's 0.2, you're using much more of the second order information, then it's extremely difficult to make those wheel nodes look more important than the central node. So this is first of all just a sanity check, confirming that we are incorporating second order information, but also allowing us to quantify, at least in this simple case, how much effect that second order information can have on the centrality measure. Okay. The next topic is going back to this clustering coefficient idea. So remember, we had the Watts-Strogatz clustering coefficient, which is a very standard concept in network science, very widely used, something that's measured in lots of real networks, but it's not a mutually reinforcing definition. So nodes benefit if they take part in triangles relative to how many edges they have, but there's no sense in which we decide whether those triangles are important and give them extra credit for that. But with this second order framework, we can now introduce a measure which does have mutual reinforcement. So we're going to introduce another three-dimensional tensor, TC, and this has a value 1 over di times di minus 1. So this is proportional to the number of possible triangles that node I can take part in. It has that value if ijk form a triangle and 0 otherwise. So we're scaling by the appropriate quantity that the Watts-Strogatz clustering coefficient would have in it. And then we look at the purely second order version of this eigenvalue problem. So we define x to be the solution to this nonlinear eigenvalue problem. So the centrality, or in this case, the clustering coefficient of node I is proportional to this tensor operator on the vector x. So we have a definition here which is giving extra weight to nodes, which based on their propensity to form triangles, based on their degree, form triangles with other nodes which themselves have high clustering coefficients, so which themselves form triangles with other nodes involved in important triangles. So it does have that mutual reinforcement aspect to its definition. And the theorem I mentioned earlier about existence, uniqueness, and the convergence of the power method also holds for this definition. So this is another measure which can be computed with the same algorithm. Okay, so I'll stop here again. If there are any questions that could be answered now, I'm happy to do that.
Yes, there are two questions, both of Vanni Noferini.
Right.
He wants to ask the constant p. Can it be? Does it have to be real, or can you also use actually the minimum or the maximum in the computation?
I would need to check the proof. I'm pretty sure just by taking the limits that you would also get the result holding, but I'd need to carefully check the proof. Yeah, so I don't know exactly for sure whether you can actually include those limits.
Maybe also ask if it can be complex, but
right, I was waiting for that one from Vanni. Yes. If you understand what complex is, then good luck. And that's a little bit beyond me, I think. So okay. I'm not sure what application you'd like to apply a complex power mean to, but I'm happy to learn.
And then his other question is about the computational complexity. like to build the this tensor T. How easy is it to compute all these triangles? How easy is it to apply a vector X to compute Tx?
Yep. So in terms of building the matrix T, there are some really fast algorithms around. I think the worst case complexity is not great, but in practice, they're, I think, roughly linear in the number of edges in practice. So Tammy Calder has a paper on this. Maybe she talked about this in the in this series. But in practice, for large sparse networks, you can build T efficiently. In terms of applying, I mean, I guess again it's sparse matrix linear algebra. So I would hope that this would be viable in that setting. Okay,
and then there's a third one of Volker Meerman. He asks this last operator TC, is it unique, and is it related to a flattening of a more typical operator?
Is it unique? Well, yeah, I mean, I guess the definition.
Oh no, I think he means the eigenvalue. Sorry.
Oh, sorry. Yeah. Yes. Yes, it's unique up to a scaling. Yes. Is it a flattening? Yes. I mean, I guess you could interpret it that way. Yes. Yeah. And if you apply this operator to the vector of ones, then you get back the Watt-Strogatz clustering coefficient. So that's one sense in which we are generalizing this. For any value of p, you get back the Watt-Strogatz if you apply TC to the vector of ones.
Okay, that's it on Zoom.
Right.
Yeah, no question on YouTube at the moment, so please go ahead.
Right, thank you. So just a final part of the talk now where we apply these algorithms, or at least one version of the algorithm, to a real network. One of the issues which many of you may be familiar with about centrality measures is that in most cases there's no right or wrong answer. So I might tell you that this node is the most important node in the network, and you have no way of proving or disproving what I've said. And maybe you have your own algorithm which comes up with a different ranking of the nodes, and which of us is correct is a matter of opinion. There are some cases where you do have some extra information which can be used as a proxy for centrality, but those cases are relatively rare. So that's one of the issues in deriving and analyzing centrality measures. What I'm going to show here sort of gets around that problem, looking at the link prediction setting. So the context here is that the network that we're given may have some edges missing. There may not have been observed. There may be some noise in the network. So we want to fill in these missing edges. In other contexts, you may have a network which is evolving over time. In particular, it may just be growing. Maybe people in a social network are making new connections. They're friending each other in some social media website. So new edges are emerging. New products might be being purchased in an online setting. I'm sure you can imagine that it's useful to try to predict where this new activity is going to take place. And one idea for making those predictions is to look for unconnected pairs which somehow can communicate with each other. For example, they've got lots of nearby interactions going on. And that's, in essence, the idea behind seeded PageRank. And we're going to generalize this to make use of higher order information. So I'll first of all describe the seeded PageRank iteration. So for every node L, we look at this iteration. So this is the PageRank iteration, thinking of it as a random walk. We're randomly walking around the graph, and we're teleporting to a particular node. So EL here is the Lth column of the identity matrix. So whenever a teleportation step takes place, then we always jump to node L. In the voting context, we're sharing out the votes, but node L always gets a little bit extra when we do that. So L is a distinguished node. The steady state of this iteration will denote by X brackets L, and it solves this linear system. And then the seeded PageRank similarity matrix is then this symmetric matrix given by this combination. So first of all, we look at the proportion of time we spend at node J, given that we're always teleporting to node I, and then vice versa with the I and J swapped. So this is telling us something about how well connected nodes I and J are. If you keep jumping to node J, how much time would you be spending at node I? Tells you something about how well connected they are, going beyond simple pairwise edges. So we build this matrix, and then whenever there's an edge missing, we predict that the edge should be there with some probability proportional to the value Sij. Okay, so the most likely edge that's missing is the one with the highest probability. Okay, so in a sense, we are taking walks, we are going beyond pairwise, but I want to build that information more directly into the process. So we're going to extend this to a second order iteration. So here, we're now going to do this type of iteration where we have this new term, and there's a linear combination, a convex combination of the previous random walk on the graph type term and another term here which is using the tensor operator. So this is giving extra benefit to node I if it's involved in triangles with nodes which are currently given a high value in the iteration. Okay, so we're adding in an extra term which is building in this second order information into the iteration. And we normalize, and the theorem that we can prove says that this is guaranteed to converge to unique positive solution. And in the similar way to what we saw on the previous slide, we now build the second order seeded PageRank matrix by combining these two terms. So how frequently do we visit node J when we're jumping to node I and vice versa? And I said that we're trying to get around this idea that it's difficult to judge centrality measures. So what we're going to do here, it might be a little bit of a cheat depending on your viewpoint, but we can now take a real network and we can remove 10% of those nodes, of the edges, for example. So remove 10% of the edges and then try to predict where those removals came from. So we give the algorithm this new network and ask it, where do you think the edges are missing? And we can now compare that with what we know are the edges that we took away. So we compute the overlap between these missing edges and the corresponding high probability edges from this matrix S. So we'll do that averaging over 10 random removals independently for the network. And I'll just show you one example. There are more in the paper. So this is a network of UK faculty members, so UK academics, and this describes social interactions between academics. So I think these two down here are probably mathematicians. They've got very few friends. So taking this network, removing 10%, doing the similarity seeded PageRank matrix, looking here at the relative performance of the original, of the new method. So this is the method using second order information relative to the first order method using PageRank. So the ratio of how much overlap there was in the two cases. So a number bigger than 1 tells me that using the second order information gave me some benefit. I got more overlap with the missing edges. These are box plots. So the red lines show the median over those runs, and the length of the box takes us from the 25th to the 75th percentile. So this is for a particular value of alpha. And what I'm showing here is how this quantity varies as we change the parameter p in the power mean. P equals 1 being the standard arithmetic mean. And the main picture to take away here is that there does seem to be some benefit from incorporating the second order triangle information directly into the algorithm. So we can do better than simply using seeded PageRank. Okay. So I'm going to finish up and then I'll talk about that Squid network, just in case anybody remembers it and is still interested. What's new in this talk? Well, the idea was to take this mutual reinforcement idea, which has been popular in network science, and incorporate it into an algorithm which uses higher order information, in particular triangle-based information. So if we're given triangles, or if we want to build them from the pairwise interactions, then we can now incorporate that information directly into spectral or eigenvector type definitions of network properties. There's an accompanying existence and uniqueness theory which makes use of some very recent results in nonlinear extensions to Perron Frobenius theory. And there's a corresponding power method type iteration, which allows you to efficiently compute these quantities. In particular, we were able to come up with a generalization of the clustering coefficient, which allows for mutual reinforcement. So not only is it measuring how frequently a node tends to be involved in triangles, it also accounts for whether those triangles themselves involve important nodes. And I showed at the end of the talk how you can use these types of algorithm in a link prediction setting. There are many areas in which this could be extended. I gave some references at the start where other authors are also looking at incorporating this higher order information into various models and algorithms. We think we know how to generalize this type of algorithm to the case that goes beyond triangles to more general hyperedges. We could also look at time-dependent networks. So instead of a single network, you have a sequence of networks where the edges are appearing and possibly disappearing over time. One thing I didn't get into in this talk, I was able to avoid it because it didn't really matter for this talk, but something that's of interest to me and I think will become a debate more generally in the network science community is what is the appropriate higher order model? Should we be thinking in terms of hyperedges or simplices, or just looking for motifs and counting those in a network? So how do we incorporate higher order information? I think is an interesting question, but I think it should be driven by the application. And as I said earlier, the applications I can think of are generally most suited to the hypergraph hyperedge definition, in my opinion. Okay, so I'll just finish with this Squid graph example. Maybe if anybody wants to chip in, has anybody computed the components of the Perron Frobenius vector on this matrix?
There's no answer on Zoom.
No answer.
I think everybody
Okay.
is still computing.
Right. Okay. So it's something that we just stumbled across. We weren't looking for it, but I think it's of interest. What happens in this case is that you get exactly the same centrality measure for node 1 and for node 6 and for node 8 and therefore node 10. Okay. So I would call these spectrally spectrally isocentral, I think is an appropriate term. They have the same spectral centrality, even though they're topologically distinct. And so the eigenvector measure can't distinguish between them in terms of how important they are. Also, interestingly, node 7 and node 9 are given exactly the same eigenvector centrality. And of course, node 11, therefore, as well. So there are 6 different types of node in this network, but there are only 3 different distinct components in the Perron Frobenius eigenvector. So only 3 different central nodes. And this will be appearing just as a side remark in some forthcoming work with a couple of co-authors, Francesca Arrigo and Vanni Noferini. Okay, that's where I'll finish. Thanks for your attention.
Okay, we have one follow-up question from Volker. I will try to enable his microphone. Yes, Volker, go ahead.
Yeah, thank you very much, Des, for the great talk.
Thank you.
Yes, Volker?
That was it.
No, apparently it doesn't work. So he wanted to clarify his question about
Right.
the uniqueness of the tensor eigenvalue.
Okay.
So he says usually eigenvalues of tensors are not unique. There can be many solutions to the nonlinear equation. His question was whether the solution with positive eigenvector gives you the uniqueness.
Oh yes, yeah. That may well be the key point. Yes. So the theorem does give us uniqueness, but under the condition that it's a constrained eigenvalue problem. So we have to have non-negative. In fact, the unique answer has non-negative entries, not just sorry, it has strictly positive entries, not just non-negative.
Okay. Just for completeness, about this question of Vanni for the min and max, the infinity of the p. I think your co-author Francesco,
Right.
he answered that indeed it is possible to use this explicitly.
Right.
And I think that's it for Zoom.
Yes, okay. I think on Zoom there's also a remark of Cleve Moeller actually, that PageRank is not actually an eigenvalue problem because we know the eigenvalue is 1. It's just really finding the null vector he wrote. And yeah, on YouTube there are many thumbs up and clapping hands. No questions. So let me ask one. You first presented this centrality measure, and I'm wondering if this centrality gave you any vastly different centrality scores than Eigenvector or other centrality measures that are out there, or for what type of network would this be like really a completely different result?
Yes, there's a little bit of that in the paper that I referenced. So we do look at the correlation between standard eigenvector centrality and the new measure as a function of alpha. There's some difference. It's always difficult to quantify these correlations because do you want the whole vector, the correlation over all the nodes, or just the top 10 or the top 100? But we do have some results there, and for certain types of network, there are genuine differences. But again, this is a standard issue when people define new centrality measures. Are you looking for something that correlates well or correlates completely differently, completely negatively with existing measures? So it's always it's a tricky question to know how to sell your new centrality measure. That's why we went for this link prediction test as well. But I'd imagine anything. And also, the standard measures don't account for triangles. If you have triangles in your data and just build pairwise interactions out of them, then I think that's, we're adding value simply by incorporating the data directly. I think that's the best way I would try to sell this new approach.
Okay, thank you. And I think there's still no further questions on YouTube, and therefore I think I'll just give back to Daniel then.
Okay, thanks. Thanks also from my side.
Question actually.
Oh, there's another question on the chat. Bart, do you want to take it?
Oh yeah. So on the last slide, 21 or 22, Kai Bergerman, he asks, it seems like smaller values of P give better result. Is this true in general? And could negative values for P also have some meaning and improvement?
Looking at the other results in the paper, it wasn't a general feature. So I don't think there's any intuitive reason why taking smaller values of P should help. Yes, you can take negative values, but as p goes to minus infinity, you get the minimum of the two. In some applications, maybe that's useful. Maybe that makes sense. In some applications, you get the benefits from the least important of the friends in the triangle. So it certainly has an interpretation, and I think it depends on the application as to whether that's a sensible thing to do.
Okay, there's one more of Nicolo Guglielmi, but hidden as Francesco Todisco apparently. So it's a question of Francesco. Have you tried computing the tensor eigenvalue centrality for the Squid graph?
No, not yet. I mean, I regard this as interesting because I can't think of any way to discover a similar graph. If you put edges in, then you make a huge change. You can't just continuously vary a graph. There's either an edge or there's not an edge. So that's why I think it was interesting that it just happened to come up with exactly the same components in the eigenvector. I'm not aware of any theory about how to build similar networks.
Okay, that's now really it. Thanks.
Thank you.
Okay, thank you, Bart. Thank you, Jörg. Also, thanks, Des, from my side for your great talk. I will try now to share my screen. That should work with the lineup of the next talks. So in 2 weeks, we are going to have Françoise Tusseux from the University of Manchester. And this year will be concluded. It's probably not bad that 2020 actually ends now very soon. Was not such a great year, but the year will be concluded by a great talk by Ren Greif from the University of British Columbia. Okay, see you everyone in 2 weeks, Wednesday, 4 o'clock Central European Time.